Hi, everybody. So in this presentation, we'll talk about 2.3, which is calculating limits using the limit laws. So by now, especially in 2.2, we talked about limit and definition and one-sided and the infinity. And so please work on that first, and then that takes you to this section of 2.3. And at the end of it, I'll do some other examples, because this is one area where you'll have multiple examples. So I will do some at the end of this presentation, some examples from the homework, and of course during class we'll do some others. So hopefully we'll cover all that, right? So I'll go ahead, change the screen here, and I'll explain this. And after this 2.4, it's a concept. I'll talk about it in that presentation. But that one, the homework has like 2 examples, not much, not like 2.3. Okay, so the kind of the limit laws are kind of simple in a way. They are easy to remember because they just follow the pattern. So the limit as x approaches a of the sum, if you add 2, f of x and g of x, you get a sum. 1 plus 2 is 3, 3 is the sum. So f of x plus g of x equals to the limit of as x approaches a of f of x plus the limit as x approaches a of g of x. So they're kind of easy to remember. Same thing for the difference or subtraction, and same thing for the multiple. C is a number there. So we'll see them in examples. And the product here, f times g, same thing. Of course, the restriction applies when there is the quotient when you divide. So the limit as x approaches a of this quotient here, of course, the g of x cannot be 0. So you can pause the video, write these down, and that's the ones you'll be applying in different scenarios. So the sum law, the limit of a sum is the sum of the limits. The difference law, the limit of a difference is the difference of the limits. The constant multiple, which is that C, the limit of a constant times a function is the constant times the limit of the function, right? So, all right, so this one. The product is the limit of the product is the product of the limits. The quotient law, the limit of the quotient is the quotient of the limits. Of course, provided that the limit of the denominator is not 0. So, all right, so let's do an example. And here, it's a nice example, with the graph, so we also understand how it works, connecting it with previous section. So here, the limit as x approaches -2, and this is -2, of f of x. F of x is this one here, the red one, and g of x is the blue. So as you see, for f of x, for -2, it actually from here or here, you're getting 1, right? So this will be same. If we use it's going to be of this plus the limit 5 g of x, right? Using the rules. And the second one can be 5 times, if you apply the properties, and you bring this one down. And so it's just a matter of finding what this limit is. So for this one is 1 from the graph. And for the second one, if you're going to, for x approaches -2, this way or this way, it's approaching -1. So 1 minus 5 will be -4. And similarly, we'll do the others. So I kept it, I think it's presented here. So yeah, it's fine. So that's the way it's described. So now you want to ask yourself before you can probably pause the video and say, okay, can I find this one and can I find this one, right? So for one, as you see for f of x, yes, it's going to 2. The limit for this one, as x approaches 1 for f of x, is 2. However, there is the problem for g of x because g of x, the left hand side limit from the 1, let's say minus this way, it's going to be this -2. And if you do from this way, it means x is approaching 1 from the right side, it's going to -1. So for g of x, the limit here does not exist at 1, and that's going to affect applying the rule. So are you going to use -2 or are you going to use -1? So one way to do this, if you want to investigate a little further, is to investigate the two parts. You're going to investigate from the left for both of them and the right for both of them and see if the two outcomes are equal. If they are equal, then it exists, right? But you know, the guess here, that's not going to work. So that's what they did here is, okay, let's apply the property, which we should mention here. Of course, this is in general. So this, of course, does not say left or right, but that's, you know, it's implied there. These properties work for that, or these laws, right? As long as it's consistent. So from the left, from the graph, you'll find for f of x, you get 2, and for g of x, you get -2, right? So you go back to this graph, and if you do it, then you'll find the two numbers. For the first one, from the left, you see the left is -2, and for the other one is 2, so -2 times 2. However, for the other one is -1. That's what we already did here, right? -1. So, you know, these two are not the same, so it does not exist. The last question, it looks like for 2, as x approaches 2, right? You see g of x, the value there, g of 2 is 0. So, you know, the condition here, g of x cannot be 0. So that's the issue this one is going to have, as you're dividing by 0, so that's not going to work. So for f of x, there is a number there for 2. However, we can't use the law 5, which is the quotient law there, because the given limit does not exist, because the denominator is 0 while the numerator approaches a non-zero value. Okay. Similarly, for the power law, or even, you know, with the radical will be similar. So these laws are kind of easy because what we think is going to happen is what happens, right? If somebody says the limit as x approaches a for f of x power n, you know, we may just guess it's going to be that limit to power n, and that's, you know, that works. And of course, n is it should be here a positive integer. Of course, we work with positive integers. even for exponents, you know, when they are negative, we return them to positive. So we're not talking about negative exponents here. All right, so that's one. And so you can also apply it, the root law here similarly, right? The nth root of f of x, right? And so the limit as x approaches a of that is the nth root of that limit, right? So that's similarly is not an issue. There is something everybody kind of uses in a way, which is these direct substitution. If you can just substitute and you get a value, then it works. If f is a polynomial or a rational function and a is in the domain of f, means it does not make the function undefined, then the limit as x approaches a of f of x, you just use a direct substitution. So example, limit x approaches 1, x squared plus 5x plus 6. Here is a polynomial, right? Well, it's just going to be the limit, let's just say, let's just make it simple, a direct substitution, because we can do that. All right. So that's f of a. Here a is 1, and f of x is x squared plus 5x plus 6, and a here is 1. We know this. The limit f of x, limit as x approaches a of f of x is L if and only if from the right and left are equal. So we did this already. All right, so when computing one-sided limits, we use the fact that the limit laws also hold for one-sided limits. Right? There is something, this theorem, it's kind of straightforward, but this one is going to be the most important one that we need to know and we need to address. But this one, of course, if you think about it graph-wise, if f of x is less than or equal to g of x, and think about the y values, right? If there is a graph below this graph, right? When a is near a, or should be x near a, except possibly at a, anytime we talk about limit, we're not really taking that number, we're going close to it, just like you saw in the other examples. And the limits of f and g both exist as x approaches a. So what does this mean? If f of x is less than or equal to g of x, then of course the limit of that function as x approaches a is also going to be less than the limit as x approaches a of g of x. So this is kind of intuitive in a way to figure out. However, for this squeeze theorem is an interesting one, which in some higher math courses, of course, they do the proof and prove them. But for us, we'll use it and we'll try to understand it, and I'll give an example to it at the end. So if you have, this is to prove certain limits and show what they are. So if you're interested in this, the limit of this g of x, right? As x approaches a value, let's say you can calculate this, right? But you know the limit of f of x as x approaches that value And you know the limit of h of x as x approaches that value. And they're both equal to L, right? So it's like you have the upper bound and the lower bound, they're equal to the L, the same thing. And this g of x is in between, right? So think about this theorem too, and think about now what we're talking about. And I'll show it in the example. What does that mean? It means that this must have the same limit. It's squeezed between the two, right? It's almost like you're saying this and this. So, and the one you're interested in, something maybe like here, well, if this one is L and this one is L, then if the function you're interested in is in between, that means its limit must be L. So I'll show it in different graph, but that's what it means. So look at the lower one, the higher one, they both have same limit. That dictates the one in the middle must have that same limit. So this is what we call a squeeze theorem. And it's important when it comes to these limits. All right, and this is a graph for it, and we'll do an example. The squeeze theorem, which is of course called sandwich theorem, that's another name to it. Of course, just a sandwich because you have H the upper and F the lower, and you have G in between, and you see if for F it's L, and for H it's L, and we know that G happens between F and H, then it must be L as well. All right. Cool. So let's talk about some examples, and I'll look into the homework and solve some of them. Maybe we'll do this squeeze theorem one first. Then find some other problems after that, since we are here anyway. So a nice example, it's at the end of the homework, 2.3, question 17. So 2.3, number 17, show that the following limit is true, and it's the limit as x approaches 0 of x to the 6th and sine of 1 over x over 0. So if you investigate this, and of course if you want to do the chart, you'll find you know, something the x to the 6th and graph, and the other one, and you know, the other function, the sine of 1 over x is going to be in between, so it's squeezed in between. All right, and you can graph these and see what they are. But now let's look into what's happening. So if you look into sine of 1 over x as x approaches 0, what happens? Well, you know, as x approaches 0, even the sine value as well approaches 0, so you cannot calculate this, right? So you can't say this sine of 1 over x is 1 or 2. It's like undefined. But we know that the sine value is between -1 and 1, right? So that's kind of where you're going to start. So we know this, you know, the sine function is between -1 and 1. So we're gonna set up these lower and upper. You know, the trig function, the sine and cosine, they're both between, their range is between -1 and 1. So what happens if you multiply these by this by x to the 6th, which you want? So if you multiply this whole thing by x to the 6th, and you know this x to the 6th, this is even, so this is positive. It's not going to affect this. You're going to get negative x to the 6th less than or equal x to the 6th sine 1 over x less than or equal x to the 6th, right? Then now let's look into what is the limit of negative x to the 6th as x approaches 0, because we're interested in 0. Well, this you can use that direct substitution, right? And it's just going to be 0. And what is the limit of x to the 6th as x approaches 0? Same thing, direct substitution is going to be 0. So now, what does that tell us for this limit? That's 0 and 0, right? Then for this, it must be 0, right? So this is true. So using the squeeze theorem, we can prove that the given statement is true. Given statement is true. All right. So it's not complicated, but you will need to know this idea of a trick to set it up as the squeeze theorem, and then it works. All right. So now let's look into maybe some examples. I'll try to use the ones that have to do with this, because maybe in class I'll do the ones that have to do with other tricks, whether you're using the conjugate or something else, or you know, stuff like that. So let's look into an example. There are many that in which you graph, so you need to, you know, kind to review your graphs and how you do the graphing and stuff. So yeah, so here is let's pick this difficult one a little bit. So we will keep this lecture video towards the difficult ones that go with the concept and the tricks that are probably just new to you in this course. So for example, number 13, and it says you have a limit of x approaching 1 of f of x minus 6 x minus 1 equal 4. Evaluate the limit of the function f of x. I have a different way of doing this. If somebody's interested, I'll show it later on in class. But you know, if you're using the resources with the book and stuff, you may see a different one, so I'll explain that one. What this other one does is it tries to trick this to, you know, to explain it. So you're given this. My other way is math oriented. This one probably is like a proof type oriented. So this, what it does, it just says, let's play a trick on this. And you're gonna use this method all the time on these. F of x minus 6, all right. We need to find what this limit is. We don't know. So, okay. So we can do like we usually do. you multiply up and down by the same thing, which doesn't change anything, right? And we know that the limit, using the rule we talked about, or the law of the limit, then this is going to be, because this is the product of x minus 1, and this one is given, this one is given as 4, and this one is direct substitution, 1 minus 1 is 0, so it's 0. So the limit of this numerator here is 0, right? So that's one way to trick it. And now that we know that the limit of this f of x minus 6 is 0, we can use the law of the difference to split it. Right? And what do you think is going to happen? So what is the limit of 6 as x approaches 1? It's just going to be 6, right? So what is the limit? So keep in mind, this is what you have, right? The limit of this equals 0, right? So now this is this part here. So for this to be 0, the limit of f of x must be 6, right? So we started with this part right here. We tricked it by multiplying up and down by the same thing, which gave us the one we have, what's given, and this one can be calculated. So it gave us this part here as that, and we split it into two terms, subtracted, and the result has to be 0. And if the result has to be 0, that tells us that the limit of f of x is 6. All right. And these you'll use same method all the time. And I'll probably solve a different one in class. Let's see, what else? We can do, yeah, we can do another squeeze style question. Number 9, let's look at number 9. It says that if 3x minus 2, just to show that f of x for x greater than or equal 0, find the limit of f of x as x approaches 3, right? So x approaches 3, that means you're interested to know what is the limit as x approaches 3 of 3x minus 2. And same thing here, what is the limit of x as x approaches 3 of x squared minus 3x plus 7. So it looks like we can substitute in this one and this one, right? So we get 3 times 3 is 9, which is 7, right? And here as well, a 7. So if you have a function that's stuck between 7 and 7, then it must be 7, right? So that gives us that the limit of f of x as x approaches 3 is going to be 7. So that's the idea of the squeeze theorem, right? So in this example, we don't know what it is, the function f of x. In the first example, we know it's sine of 1 over x, but we have problems calculating it, and you know, we use this method. All right. So last example, what we need to watch for. We need to watch for the two sides, and we need to watch for if it's a rational expression to simplify. Okay, so let's do example 3, and we close this one. Number 3. So limit of as x approaches -1. So this is the value -1. As x squared minus 5x minus 6. With these always, you want to see it's rational. So you want to see if it's in simplest form. In simplest form means, let's factor and see if anything cancels. Two numbers multiply -6, they add to -5, so -6 and plus 1. This simplifies. So x over x plus 1, the limit as x approaches -1. You see, so this is the simplest form. That's you can graph this one. If you're not sure, I think you should graph it. This is a rational expression or a function, the numerator and the denominator. So please review rational functions, and of course the graphing, which has the 3 different parts, and you'll have vertical asymptote on -1, and here the same, so 1. Then you graph, then you're going to see what happens with the limit, and of course when you use the value -1, it's -1 over 0, so it doesn't exist. You know, we will go one way like this here, and we will go one way here. So, all right. Thank you. I'll stop on this one, and we'll do more examples later. Thank you.